Hello, Link 341. In today's lesson, we will talk about basic acoustics, and this is just a short introduction into what we need to know about acoustic phonetics. We will be continuing our conversation in the upcoming lessons as well. All right, so first things first, what is a sound, right? Sound is um, an item that we need to discuss in acoustic phonetics. And of course, we say that a sound is a pressure variation that moves out in waves from a source, right? I am, for example, a source, and some sound is moving in certain pressure variation to the target, and the target is this computer or your ears, right? Um, Air is pretty chaotic, right? There is oxygen, there is nitrogen, there is argon, and some other pollutants out there, right? Depending on how much we pollute the air. But the movement of air particles is unpredictable, it is chaotic, right? When we produce a sound, we shape this air, shape the molecules of air into certain mold, right? We make it, we make a pattern. We make a pattern of pressure variation, regardless of whether this pattern is really precise, like in vowels, for example, and periodic, which we will find out more about very soon, or aperiodic, as in certain consonants such as s and sh and f and so on. Regardless of that, it is some kind of a pattern of air pressure variation that moves out in waves. And it moves out in waves because we call, of course, sound, and we often refer to sound as with respect to sound waves, because they assume the shape of waves, and they move in certain direction, which I will show you in a minute, right? Sound must be within the ranges to which our ear is sensitive, and we'll talk more about that maybe in the next lesson or the lesson after that one. Our ear can capture certain types of frequencies, but our ears are not sensitive to very low frequencies that we cannot hear, or very high frequencies that some animals can hear and we cannot. So our ear has a range of frequencies, and our ear has a range with respect to loudness, so we cannot hear very silent sounds, and we are of course unnerved by very loud sounds, right? And finally, normally we talk about sound waves traveling through the air, right? So when we refer to sound, we talk about sound waves traveling through the air. All right, so yeah, what does a sound look like, right? That's the next question. Air consists of floating molecules. They're most likely widely spaced from each other. So they are spaced from each other. Generally speaking, as I said, their movement is unpredictable. However, when they're in atmosphere, they are around, right? And when you make a sound, the molecules start a certain pattern, right? And they sort of become evenly spaced apart from each other. As soon as you make a sound, they make a shape, some kind of a shape, right? And if I were to receive, for example, from this window, a magical sunlight beam or beam of sunlight, I might even see some particles of air moving around, and you probably experienced that. But when we speak, we turn the activities of air molecules, the chaotic activities of air molecules, into pattern movement, that is, into sound. In reality, these sounds move in 3D, right? But I've made here like one dimension, sort of speaking. And what do you think will happen if we push one molecule, if we push this molecule into this direction, right? what will happen? And think about, for example, pushing someone from a swing, right? Or pushing, or if you played pools or billiards, or snooker, whatever you're calling it, you know that if you put balls in a row and you hit them with another ball, what will happen, right? What will happen to this ball that you hit them with and to the rest of the balls? And that's practically how the sound travels. So the force with which you knock this molecule against its neighbor will move to this molecule. So the force from this molecule, okay, this molecule will move to that one, right? And then this molecule will move to this one, and the force will, and the energy will transmit, right? It will transfer to another neighbor or to another molecule, and so on and so forth. But what happens with this one? Well, the first one that you knock the molecule with, the other molecules with, will go past its initial rest position. So it was here, somewhere in this vicinity. You knocked it and it went to another molecule, but it hit this molecule and it went back, not to the initial rest position, but way past it, right? It went back here. And you can think about a swing, right? As I said, a swing, when you, let's say this is some kind of a swing, and you push someone, they go like this high up to the maximum distance they can go, but they come back, right? And they do not come back and stop here, right? They come back and go way past its the initial rest position. Until there is some energy, they'll do that, right? And that's one cycle, right, of a sound, or how sounds move. All right, so the neighbor in turn gets knocked against its neighbor, as we saw, and the first molecule bounces back past its initial rest position. And you can check out some atomic bomb videos. I won't play them right now, but it's basically the same, although atomic bombs have so much energy that they can destroy planet practically. But if you release, or if some smaller atomic bomb explodes, it will produce such waves of air that they will knock down some trees, but other trees at the borders of this energy will move in waves like this, right? Until there is some energy left. If there is no force left, they will go back to their initial position. All right, so the initial force gets transferred down down the line, right? And we receive the rest position number 1 and the rest position number 2 in these places. The first two molecules swing back to meet up with each other again in between their initial rest positions. So basically, when you hit one molecule, it hits another molecule, but it goes back and they will meet again in between their initial rest position, as I said, until there is some energy left. So how the sound travels is an interesting question, right? And the question we are trying to answer right now. Sound consists of these molecules of air traveling through space, and you can think about it as a water brigade. So imagine this is a bucket of water, and imagine there is some fire out here, right? the best drawing of a fire, but imagine this is a fire, right? And something is on fire. You want to extinguish this fire, right? You have buckets, lots of buckets here, but you don't want to move all the way to the fire, right? You don't want to move the bucket all the way there because you lose some time. You cannot move the fire to the buckets. So what you're gonna do, right? Let's say you have lots of people out there, and you can perhaps have one man here. Sorry for my drawings. Another man here. Another man here, and lots of people in this row, right? Until you reach the point where the fire is causing havoc, right? So what you're gonna do is grab this bucket. The first person will grab this bucket and they will move it to another person. Then this person will hand over the bucket to another person, and so on and so forth until the bucket reaches the fire. And what you're doing is basically repeating the same motion like this, right? Swaying a little bit, okay? Fire, and that's a bucket brigade. That's what they call bucket brigade. And why is this good analogy? Well, because you are not specifically moving you yourself, but the buckets are moving, and the bucket is a sound. And essentially the molecules of air will move a little bit around, right? But the molecules that are reaching your ear will be this bucket, right? And that's the analogy that we want to have here. So initial molecules will move the rest of the molecules until those ones closest to you reach your ears. And that's what we want, right? And this is a simplified version, of course, simplified sketch of the movement of sound, but think about it as a pattern that keeps repeating, and if you hit one, it hits another and another and another, and then transfers all that energy towards another or the last one in the line, which hits the target, right? And that's how we perceive sound, right? The sound molecules create waves, right? Because they resemble the movement of a wave, right? As I said, the movement of a wave is repetitive. So you have one wave, then it goes back a little bit, then another wave, it goes back a little bit, and another wave, and so on. And essentially, you don't get the movement of such a huge movement of a wave, or a single wave reaching your ears, but it's a wave reaction that is actually causing the airs to reach, or the air molecules to reach your ears or the target. Ultimately, individual molecules vibrate, as I said, back and forth around an equilibrium point, right? Around here, okay? And the transfer of force sets up what is called compression wave. So what happens here is that when the initial molecule of air reaches its neighbor, the air here, or the space, gets compressed. So it's compressed, right? I'll just write like this. But here we get something that we called rarefaction or rarefication of air. So the air becomes rare, right? What gets compressed, as we know now, is the space between. So it is the space between the two molecules, and this causes what we call, compression wave. And again, we meet with the areas of high pressure and areas of low pressure. Because the space is squeezed, you get the area of high pressure, right? And because the space is rarefied, or we get the rarefaction, there is a low pressure in this uh, areas, right? Or in these areas. Compression waves consist of alternating areas of high and low pressure, and that's what we have observed quite clearly, right? Now, I want to explain how we know about this. Well, how do we know that this is what happens, right? Well, we can use pressure level meters. In the past, before the invention of microphones, we used pressure level meters, but today we are using microphones, right? Microphones consist of diaphragms. Diaphragms are thin layers that are composed of certain material around them, right? And they are usually composed of some metal, because metals are good transducers. If they're produced of golden plated metal, then we get a great transducer. When the sound reaches the mic, so I'll show you here, perhaps because I have a mic. When the sound reaches the mic, right, sound travel or sound waves reach the mic, it causes the diaphragm inside to vibrate, right? And it passes this diaphragm passes the energy to the rest of the microphone's components, which are inside. And there is a coil, round thing, right? Spiral thing, and a steel tube and a magnet that translates the energy into electric signal. And the electric signal is captured here with a cable. I have a cable for it, which I insert into computer. If the cable is of low quality, the sound might be of low quality as well, so pay attention to that. Microphone also has this membrane, stretched over it as it's all and resembles a drum, right? As if it's a drum, in order to reduce the noise, right? Microphones can be divided into two groups. This is a condenser microphone. There is a dynamic microphone used by singers. Condenser microphone is used in studios, right? And it's static, right? We use it when it's static. It has to be placed somewhere, and you don't want to move it because it captures every fine detail of the sound or what's going on in the atmosphere. If you would use it in a concert, it wouldn't be good, right? Or it would be too good because it captures everything. So you want a dynamic mic that singers are using usually for singing. If you're recording in studio, though, you want the condenser mics, and they are usually hanging from the ceiling. Yeah, what I want to show is as well, and something that might interest you, and we'll talk about this more, is a pop filter. A pop filter is a piece of cloth that is penetrated with little holes, right? So that the sound waves can travel safely to the mic. So if I talk like this, they are traveling safely to the mic, but what I am precluding from reaching the mic are the sounds that are plosives, such as b, p, mainly b, p, but also d, t, and k, g, which can disrupt the signal produced overall because of the high air pressure, because of this release burst, right? So we get sometimes this release burst that cannot be captured by mic, as if we are touching the mic like this, which is never good for your recording. So this is a pop filter, right? All right, mics, as I said, have diaphragms which move back and forth with air pressure, so they are vibrating and transferring this vibration pattern into the magnet, and the magnet does the work later because it transfers this energy or force into electrical voltage. We also have ears, right? Humans have ears. We have to be aware of that. And we use our ears, right, for perceiving sound. What ears have, or ears consist of outer ear, middle ear, and inner ear. The sound travels and it goes through this tube or ear canal, and it reaches the tympanic membrane that we call eardrum. If you pick your ears, you won't reach it, and you shouldn't reach it because then it would be dangerous. It should be left alone, right? There is some ear wax here, of course, to keep your ears dry. But if there's too much earwax, then you might not hear very well. Anyways, the sound or the air molecules reach the ear, and this tympanic membrane starts vibrating or moving inward and outward due to the air pressure variation in sound waves, just like the membrane of a microphone. The movements are then transferred to the middle ear and to what we call ossicles, the three smallest bones in your body, and these are malleus, incus, and stapes. Malleus is called hammer, incus is called anvil as well, and stapes is called stirrup. The sound waves are transferred from malleus to incus, from incus to stapes, and from stapes to cochlea. Cochlea is in the inner ear, and it's a spiral-shaped structure that transforms sound waves into neural impulses, which pass through the auditory nerve. Here it is, the auditory nerve, into the brain directly. After that, we don't know what happens, but essentially we experience fluctuations of air pressure as sound, right? What happens in the brain, how we perceive speech as speech, there are some hypotheses and theories, but still a conundrum. We don't know how the brain works exactly. Right, so that's how we know what happens, okay? So let's say we have a pressure variation in time, and we have some pressure level meter. Let's say that's a microphone. So we have a microphone at the end of it, right? So this is where it starts, a starting point right here, or where the where the one molecule, or molecule number 1, pushes the molecule number 2, then this one pushes the molecule number 3, and they molecule number 1 and 2 meet again, and so on and so forth. The pattern is repeated through time, and this is a time, some kind of a time frame. And then we have a pressure level meter at the end, or the microphone. How would we know, how would we measure the pressure, right? How would pressure change over time? That's a question we want to answer. And I'll answer it by introducing you to what we call a sine wave. I'll stop here and try to record the video in a different manner because I want to show you something in Pratt. What happens here is that, let me just play it from here, is that this is a sine wave. The reading on the pressure level meter or microphone will fluctuate between high and low pressure values. In the simplest case, the variations in pressure level will look like a sine wave. And this is one example of a sine wave, the simplest wave there is. And this is how it sounds, right? So the pressure is shown on this y-axis, and the time is shown on this x-axis. So basically what we get here is what we call the amplitude on the y-axis and time on the x-axis. So the pressure is highest here, right, at this point, and lowest here at this point. That's what we get when we have compression and rarefaction. Compression, rarefaction in the sound waves. Um, and we say that this cycle repeats, and if repeats in a single or with a single molecule wave or just a single sound wave, we call this sine wave or basic component wave. Right. Let me see if I've missed something. No, that's approximately it. The other basic sine wave concepts are the following. Sine waves are periodic. They recur over time. You see the same pattern happening over and over again in a certain in certain patterns, right, or in a certain shape, which would be different from a more chaotic pattern, which would make an aperiodic sound. And we will talk about aperiodic sound. So yeah, you can see here that it repeats. One cycle repeats, another cycle repeats, and another cycle, and I'll show you how you can check, well, where's the cycle beginning and ending, right? The period is the amount of time it takes for the pattern to repeat itself. I'm missing for here. Yep, no, not anymore. So period can be calculated by using this formula, 1 per frequency, and the frequency is the number of times within a given time frame that the pattern repeats itself. Frequency is 1 per period, right? Usually measured in cycles per second or hertz. Most of the time we find hertz as a unit. Yeah, so basically the period tells us the amount or the time needed for a cycle to travel, right? For one wave to occur. Frequency tells us how often this cycle is repeated through a certain or within a certain period of time. We usually use 1 second, right, to be able to calculate some more complex waves. This is the frequency can be thought of as, for example, how often do we have classes? Well, we don't, right? But in principle, 3 times a week, and a week is a huge period. This happens much faster, right? Finally, we have the peak amplitude is the maximum amount of vertical displacement in the wave, so maximum amount of pressure in the wave. This would be a peak amplitude here, and this one as well. We usually use this one as the max amplitude, and min amplitude is the one on the bottom, but essentially they have the same values, but the minimum is the negative value and the maximum is a plus value. When we calculate later, you'll see how we can calculate something that is called RMS. We will transfer everything into positives, right, to make it easier for us. But you can say, okay, this is the peak amplitude here, minimum or maximum of the amplitude or the pressure that the sound reaches, right? So the maximum amount of compression and the minimum amount of compression. And when this cycle is repeated, or this pattern is repeated in the same way, we have a sine wave, or a simplest case of a sound wave. Right, so we've already talked about period and frequency in our last class. I want to show you a waveform that is plotted here. This is a waveform, one waveform, and this is the time and amplitude, right? We don't have any scale for amplitude here, right? I don't know, it can be, let's say 3, right? 3 something. Amplitude is equal to intensity, but we'll learn about intensity more, or perceived as intensity, and we'll learn about intensity in several weeks. Right now, what you need to know is that the amplitude is air pressure value, right? At certain point. So if I choose this point here, I can say, oh, the amplitude is this much. Or if I choose this point here, I can say, oh, the peak amplitude is that much, or that value. A cycle is this. So the movement starts from 0, and then there is a highest compression because the molecules hit each other, and then there is a swinging back of molecules to their initial position, right? And way past this position because of the energy. Way past this position. And think about the swing, pushing someone a swing. And when you go way past your position to the maximum or minimum distance, in this case, negative distance, you go back to the initial position or to the 0 position, and this is one cycle, and it happens in 0.01 second. So let me calculate something again, right? You know how good I am with calculators. So we said that the time is 0.01 second. If we take this time or period and want to calculate frequency, we can do this 1 by 0.01, and we get 100 hertz. So 100 repetitions in 1 second. We get 100 occurrences of the cycle of this one cycle, right, in one whole second. And this is only 0.01 second, right there. And yeah, that's, I guess, easy to understand, or relatively easy to understand. Hopefully this of course makes sense. When more than one sine waves or sine wave gets combined, so 1 plus or 2 or more, right? 2 plus, I'd say it's better to use 2 plus, we get what we call complex wave, right? At any given time, each wave will have some amplitude value. This is not difficult, just the denotation might be a little bit confusing. So A1 or A sub 1 indicates the amplitude value of a sine wave 1 at time 1. So at some time, right? At some point. A sub 2 indicates amplitude value of sine wave 2. So we are adding another sine wave at the same time, at the same point. So imagine this is a sine wave 1. So we have S1, sine wave 1. And we want to add another sine wave to get the complex wave. So this sine wave 1, and we want to use, for example, amplitude at, I don't know, peak amplitude maybe here, right? At around, I guess, 0.0025 maybe. Like a half, right? 25. We have this amplitude value at this time, 0.0025, and that's some amplitude value. Let it be, it's 6, right? 6. Then we add another amplitude or another sine wave, and we see we have it in some image. Let's say you have some image, and you see, okay, the amplitude value at 0.025 seconds is, let's say, 3. So we add up these and we receive complex wave. The amplitude value of the complex wave is the sum of these values. How this works, let's see. So yeah, I'll first maybe show you in prot. So let's say I'll do this, remove. Let's say I have prot window here, and I want to create a sound. So you can click on new sound, and you can create sound as pure tone. Sine waves are also called pure tones because of the periodicity with which they repeat. Um, Now this sound will have a frequency of 440, sorry. We won't change anything. The amplitude is expressed in pascals. We don't have to worry about that right now. It's like pressure, right? Pascals. The starting time 0, 0.0, the end time, I can have it 1 second, right? So 440 hertz, 440 cycles per second. And this is how it will look like, right? Now this is, you can see that there is some repetitive pattern, but if I close it in, oops, maybe a little bit more so, big one. Okay, you see a lot of repetitive patterns, right? So in, right, we have 1, 2, 3, 4 of these in 0 0.007 or 6, right? It doesn't really matter, but this is just an example of a pure tone sine wave, which is repeating itself periodically in equidistant shape, right? Shaped waves. 440 times a second. So this is how it sounds. It goes by very fast because it's only a second, right? All right, so this is how you can create a pure tone. I might want to maybe create a sine wave from a formula. Okay. Yeah. I'm thinking whether to do that right now. Okay, I can do that right now. Why not? So let's keep it. So this is the standard. This is how you would open this. This is how you would receive it. If you click on New, Sound, and Sound from Formula, this is how you would receive this window. So this here indicates the time, right? This is 0.5 seconds. And this here indicates the frequency or hertz. We don't need this random Gauss noise. I'll write it like this, 0.5, and the hertz, right? How many hertz? We have 100 hertz in what was in 0.01. That's very quick. That's very quick. 0.0, oops, 0.01, right? Okay. Yeah, you cannot even hear it. Because it's very low. Okay. Let's see if I increase this one. Yeah, it's a low sound, right? And that's why it's you can hear it like that. Right, so this is how you can create a sine wave for from the formula. As I said, when you add the amplitudes up, you receive a complex wave, and this is an example of a complex wave. So for example, take waveform 1. There is high amplitude and low frequency. This means that we have high amplitude, it goes to 1 and -1, right here, but low frequency, because these repeat it themselves only 4 times, right? So 1, 2, 3, 4. Now we have waveform 2, or sine wave number 2. These have much higher frequency. They repeat themselves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times, here 4 times, in how much? I don't know, 0.5 seconds, for example. But we have low amplitude, much higher frequency, but low amplitude, amplitude of 0.5 here, right? Okay. All right, so we have that one. Yeah, sorry about this. I said something, so I have to correct myself. New sound from formula. This is actually amplitude, 0.5, not the time. Okay, so we have the start time and end time. It's 1 second. My apologies. Anyways, so this is the amplitude here. All right, amplitude. Not that write anything because it won't do anything for you, but I'm writing here frequency for 100 hertz, right, per this amplitude. Now let's create these two, right? Let's create first this one for 4 hertz, which we want probably here, and the amplitude can be 1, right, in 1 second. All right, it's like some noise, right? It's very low, right? Okay, and let's now create the second one. 12, 12, 12, and 0.5, because remember 0.5 amplitude pressure goes that far per 12 repetitions. Again, too low for our ears to observe anything. Usually the boundary of hearing something very well is 20 hertz, right? Or 20 decibels, sorry, 20 decibels, and this is the frequencies are similar to this. Yeah, we don't go that low, it's just noise. Right, so how do we get a complex wave? Well, adding these two waves. Let's create a new waveform formula. So we have 0.5. So this is the second wave, and this would be the first wave, 4 and 0, and this here 1. So amplitude 1, 4 hertz, amplitude 0.5, 12 hertz. That's the first and second sine wave. If we add them up, see what happens. We get this guy here. There is some kind of vibrating sound there, because it's not just one sine wave, we have two. We get this complex waveform here, right, which we saw in Prot. Okay, here it goes. All right, I think that's pretty clear and easy to do. What about these examples here? So we have a tone or a sine wave of 480 hertz. It sounds like this. When we combine it with 620 hertz tone, what do we get, right? So what would you get from these two? I guess the combo would be the dial tone. Basically, you know, when the telephones, all telephones, each one had its own dial tones, and they were just made by adding these two up. We can maybe try with the formula here. So we have two of these, so the second one is 600. I'll have the same amplitude for both, 0.5 for example, and the first one is 480. and we get this pattern. Oops. Yeah, so that's the pattern that we get. When the phone is not available, or when a person is not available, you hear this on the phone, right? Uh, and this is the pattern that we received. Yeah, fairly easy to do that in prot. Um, so the fundamental frequency. So as I said, why are we talking about all of this? Okay. Well, there is something that we call the fundamental frequency. The fundamental frequency of a complex wave is the frequency at which the complex wave repeats itself. Um, we've seen the cycles and the repetitions, right? Basically, the frequency of the cycles is the fundamental frequency of the complex wave. And it can be calculated by using the greatest common denominator of frequencies of component waves. Um, Component waves or component waves are just sine waves, simplest waves. And when you add one sine wave and the second sine wave, you get a complex wave, right? And the greatest common denominator, if you like math, is the largest number that the two numbers can be divided by to yield an integer whole number value. Now let me show you what this is. It's not so difficult really. So if we want to find out what's the fundamental frequency of a complex wave consisting of 600 hertz and 800 hertz, how would we do it? Um, as I said, you have one wave, sine wave, another sine wave. Each has its own frequency. When you add them up, then there is a different complex wave. This complex wave has its own frequency, and we call this frequency the fundamental frequency. So what's the fundamental frequency of complex wave consisting of 600 hertz and 800 hertz? Now we know how to calculate. Just use the greatest common denominator of these two numbers. So you would probably say, for example, let me insert this one, 600 and 800. Can we divide these two numbers by 600? No, I don't think so. Can we divide these two numbers by 400? No, really not, because 600 cannot be divided by 400. Can we divide them by 200? Yes, and that is the greatest common denominator, or the greatest number that you can divide these two numbers with. So 200. Let's give it a shot in prot. So sound from formula, we already have 601. Let me change it, maybe 800. Oops. And we can have here 600, and then we can have the same amplitude. We receive this. Did I add it? Maybe I didn't. Okay, do it again, maybe complex wave this time. All right, here it is. Yeah, so it's around 200. It's still a periodic, so it's repeating its cycles in certain pattern that is quite observable here, and you can count these spikes or these cycles that are being repeated. So we get a 200 hertz waveform. If we show pitch and we perhaps get pitch, it will be like 200 hertz, right? We'll learn about pitch more, but in the next slide I'll explain why fundamental frequency is so important. So basically, if I increase this and we get So this would be one cycle, I guess. Yeah. So 0.005 for one cycle. Let me open the calculator again. That would be 1 per 0.005. That would be 100. And we get the fundamental frequency, or the frequency of this complex wave, right? How about the one with 120, 150 hertz? I think you guessed it right. What is the greatest common denominator for these two? Well, it's 30, right? 30 hertz. If we do the same with this one, sound from formula, complex wave number 2, we want to have here 150, and bear in mind these are lower values, so you won't probably hear these so well. We got something like this, right? Still periodic repetitive pattern, and here is the, yeah, okay, let me play this whole. There's some kind of vibrating low sound, right here. And if I get, show pitch, maybe get pitch, it's, yeah, undefined, because, okay, here get pitch, it's 137. Yeah, something not right here. It's not reading it well, probably. Let me see whether I did this correctly. No, it's good. It's good. It shouldn't be 137, right? Yeah, not good. Let's see. So one cycle, right? 0.025. One. Okay. 40. Okay, we're in the ballpark here. But 30 would probably be the greatest common denominator, or the fundamental frequency. I don't know why Pratt is not cooperating with me right now, but it should be. And this is a very low frequency. Maybe I didn't set it up. Yeah, sometimes that can happen. I have to go to pitch settings and set it up to read the amounts below, right? Like 20, okay? And here it is. Okay, so I made that mistake, and I'll teach you how now to do it. So here it is now. If I maybe select this part here and get pitch now, it will show 30 hertz. Much better now. Saved by the bell. Okay, this is a fundamental frequency, and linguistically speaking, in speech, the fundamental frequency of voice sounds is based on the rate at which the vocal folds open and close. So fundamental frequency shows the rate at which your vocal folds open and close. The wave set up by the vocal folds is a complex wave, of course. So, for example, the combination of 100 Hz and 300 Hz wave would look like this. But voicing of your vocal folds is even more complex, because they're not strings, right? They're tissues, and they are like folds. That's why we would call them folds. And it's not so periodic in terms that it's so well shaped and properly shaped like here, right? It looks more like this display, and this display is an example of placing electrodes around the larynx to capture the vocal folds vibrating. So you place them here, and then you capture them vibrating with, I think, what's called EEG, and this is what they look like vibrating. It's still periodic, There is some repetition of the cycle, but it's not so well shaped as in a pure tone, right? Why should we care for the end of this lesson? Why should we care about the fundamental frequency? Well, fundamental frequency in speech, as you could see, I was measuring something that we call pitch, pitch and get pitch. Make sure to properly set up your pitch settings, pitch range, which I didn't, that's why I didn't read it first. But pitch is what we perceive in speech, right? Some languages have tones, some languages have pitch accents, some languages have stress, all languages have intonation, and we measure fundamental frequency to determine whether the tone is high or low, whether the pitch accent is high or low, or rising or falling, whether stress is moving in certain direction, whether the pitch is moving in certain direction when somebody is producing words with certain stress, such as contrast, right? So fundamental frequency has this linguistic meaning, which is very important because tones, pitch, accent, stress, and intonation are part of languages of the world. Since the modulation can occur independently of the stream of vowel and consonant segments in speech, these linguistic properties are often referred to as suprasegmentals. So we say for consonants and for vowels, they're segmentals, such as a, b, g, d, right? And some clicks that we learned about, trills, and so on and so forth. But voicing here, and not just voicing, phonation, the use of vocal folds can occur most of the times independently from producing vowels and consonants. So we can produce different tones and say the same segments, such as I talked about this example when your music teacher wants you to do this in rehearsals. They want you to sing like in a low voice, such as la, or in a high voice, la. But what I'm doing here, I'm producing the same set of sounds segments, but I'm producing different suprasegmentals, and that's why they are called suprasegmentals. They are somehow above segments in this way. And they have this linguistic meaning, which we will learn about. So this was the introduction to basic acoustics. We learned about sounds, we learned about sine waves, we learned about complex waves, fundamental frequency, something that you should know about for sure. And we will continue this journey on acoustic phonetics, which is really exciting branch of phonetics, in our next class. Until then, stay safe.